Hello, welcome to another Cosmology talk. This week we have George Zahariade, who is a postdoc at the Beyond Center at Arizona State University. He had a very, very interesting paper recently that was doing something that is like the holy grail of science, which is talking about a way that one might detect quantum gravity, more specifically how one might measure the quantum nature of gravitational waves. So this is a little bit outside the realm of normal cosmology. So as a result, George will keep it at a sort of general technical level. So the level of this talk will be maybe a colloquium level rather than a seminar level. Thanks for coming, George. Do you want to start off by telling us a little bit about what is done in the papers, I guess, that you'll be talking about today?
The idea is that the theory of gravity described by Einstein's theory of general relativity is a very successful theory, but it's a very classical theory as well. And it doesn't mesh very well, it doesn't mesh at all with quantum mechanics and quantum field theory. In particular, for example, if I have an electron and I split its wave function in two, like kind of a bimodal wave function, what is the gravitational potential of that distribution? Does another electron or some massive particle get attracted to the center of mass of that bimodal distribution, or does it get attracted to one side or to the other? So that we don't know, because general relativity is a classical theory and does not deal with these things. The best we can do in general is to consider that general relativity couples in some semi-classical way to the average value of the quantum averages of whatever other quantum fields exist in the universe. But we know that that is not very satisfactory. Although we know that gravity does not mesh well with quantum mechanics, we have zero at this point experimental evidence that gravity is quantized. It should be quantized because on theoretical grounds, but we have no observational evidence for that. So what we are trying to do in this paper is answer exactly that question. Is there a way in which we can observe quantum effects in gravity, and in particular in gravitational waves at gravitational wave detectors?
When you say we kind of, in some way of doing calculations, we model it as if it's the average value of the quantum field that sources, say, the gravitational potential or the curvature of space-time. Does that not lead to almost immediately kind of like non-local effects? Because I'm just jumping in here because I don't think I explained my thoughts perfectly in the conversation with George. I do think he understood my point anyway, so I'll leave in his reply as it was. But the point is that in quantum mechanics, the expectation value of, say, the density of the field can change suddenly when you make a measurement, which is very messy here. For example, if gravity couples to the expectation value of the field, then the gravitational potential can suddenly and dramatically change when you make a measurement. E.g. in this superposition example, if you've got one piece of the wave function here and one piece of the wave function here, before you make the measurement, your gravitational potential is centered here. As soon as you make the measurement, and suppose you make the measurement and it shows up here, suddenly the gravitational potential instantaneously changes from being here to here. Now, if gravity is itself in a superposition of a gravitational potential here and a gravitational potential here, everything's fine. It just collapses into the gravitational potential here or the gravitational potential here. There's no instantaneous change in the gravitational potential. And so if you do have this coupling to the expectation value scenario, then you get the problem that you can kind of send messages faster than the speed of light, which doesn't happen in ordinary quantum mechanics, because if you're sitting here, you're sitting in a gravitational potential. And as soon as the measurement is made and it collapses into thing here, suddenly your gravitational potential instantaneously disappears. So you know someone made a measurement here.
I agree. I think that's exactly the problem with this so-called semi-classical approach to coupling general relativity and quantum fields. It's exactly what you said. Clearly, if we take the quantum average in a state that is not a simple Gaussian state, we'll get something that looks completely wrong. The reason why most of the time it works is because most of the quantum fields that we see in nature look classical in some sense. These quantum fields are in very special states that are called coherent states. And those coherent states are well behaved in some sense.
Okay, yeah, it's hard to get something that will seed a gravitational field that is in a very, very unusual quantum state. You can't get like the sun in a superposition of here and here. If someone's remembering this talk a month from now, or remembering having read your paper a month from now, or 6 months from now, what two simple things would you want them to be remembering?
The first thing would be that our prediction is that at a gravitational wave detector, a gravitational wave interferometer, the quantization of the gravitational field should imply the existence of an additional source of noise that would superpose itself to all the other sources of noise that exist in a gravitational wave interferometer. But it will be a very different source of noise because it will be a noise of a fundamental quantum nature of the gravitational field. So that would be, I would say, the most important thing. At a technical level, this means that the geodesic deviation equation gets modified and becomes a stochastic equation, but I'm going to talk about that later, hopefully. The second thing would be that the characteristics of this noise depend strongly on the quantum state of the gravitational field. So we can imagine that this gravitational wave is in a quantum state when it hits the detector, and depending on the particular quantum state it is in, the noise that it induces on the signal will be different. Usually very small, but sometimes observable, possibly observable.
If you want to spend some time now going into the background of why you and your collaborators chose to do this specific calculation. And
well, first of all, the reason we started looking at this is because fairly recently gravitational waves were detected, and that opened a whole new window into physics that we wouldn't have been thought were possible before. And so we really wanted to do something related to gravitational waves. Then, of course, what I mentioned earlier is that this incredible puzzle of how to couple gravity to quantum mechanics is still an open problem, and there are very, very few actual observable avenues of probing this particular relationship. So that was very interesting to us.
do you have a good grasp of why people haven't done this calculation before? I mean, LIGO has only just detected gravitational waves over the last few years, but like if you were to talk to someone in 2008, it's not like they would have said, no, we're never going to detect gravitational waves.
That's actually a good question. For many years, partly because of a famous paper by Freeman Dyson, people thought that even if we detected classical gravitational waves, and even if those classical gravitational waves corresponded to some quantum states that looks very classical, the so-called coherent state, that coherent state would be in some sense built up of so many gravitons, so many gravitational field quanta, that measuring the effect of any one of those gravitational quanta would be almost impossible. It would require, Dyson was suggesting that it would require an improvement of something like 40 orders of magnitude in the sensitivity of a gravitational wave detector, which is a lot. So I think people thought it was hopeless. Although we do find that the effect is very small, it is not 40 orders of magnitude.
Right. But you are talking about measuring individual quanta.
Yes. So the mistake was, in some sense, maybe not mistake, but the kind of why people were thrown off was because measuring a quantum signature of the gravitational field is not the same as measuring individual gravitons, because a gravitational wave detector is not a graviton absorber. Indeed, if it were a graviton absorber, you would actually need to detect individual gravitons to say that they are quantized and not a big flux of gravitons. But a gravitational wave detector is more like an antenna, is more like an electromagnetic antenna than a graviton absorber. So there are ways of measuring quantum effects that are different from just detecting individual.
Is there something that LIGO could do differently now or in the future that is going to be useful?
What we're finding is that the signature of the quantization of the gravitational field is a noise term. I guess we would need an experiment that focuses on the noises, not on the signals.
Awesome. So do you want to get into the details now?
So let's see how we can observe quantum mechanical effects in gravitational wave detectors. So yeah, maybe this is just the usual thing where I show all the papers that came out of this work. The important thing about this work is that it's based on a very famous paper by Feynman and Vernon from '63 called The Theory of a General Quantum System Interacting with a Linear Dissipative System. In our case, the general quantum system will be, well, the system that we're interested in is the gravitational wave interferometer. So basically two masses moving under the effect of a passing gravitational wave. and the linear dissipative system is the gravitational field itself. Okay, so the outline will be very simple. First, I'm gonna explain how to model a gravitational wave detector in order to be able to do calculations and to come up with conclusions. So basically, we're going to model one arm of a gravitational wave detector as two freely falling masses. And we're going to couple that to weak gravity, so to basically to a gravitational field that contains a gravitational wave. And then we're going to quantize this weak gravitational field, use these Feynman-Vernon methods, and finally, find what the effective dynamics of the gravitational wave detector of these two freely falling masses are modified by the quantization of the gravitational field. And then I'm going to end by talking about what characterizes this noise term. So the basic idea is the following. Yeah, if I have two freely falling masses and there's a classical gravitational wave.
Can I ask a quick stupid question at this point? When you say freely falling masses, obviously they're held. They're not freely falling in the Earth's gravitational field. Is there like a time scale thing here where they're freely falling as far as the gravitational wave is concerned?
Not quite. I agree that for LIGO and Virgo, this idea of freely falling is a bit hidden. If you want for LISA, it's very transparent. LISA it's exactly, well, modulo experimental details, it's exactly three freely falling masses in a particular configuration. For LIGO and Virgo, of course, they're not freely falling. They're on these pendulums, basically. But in some sense, the plane where the masses move is unconstrained. Yeah, so if I have two freely falling masses, and there's a classical gravitational wave modeled by this tensor Hij that hits this plane transversely with a wave vector k, these masses start moving. They don't really move in some sense. They're still fixed in the proper coordinate system, but their physical distance changes. So if I measure the physical distance between these two masses, this physical distance will change, and I'll be able to extract the characteristics of the classical gravitational wave from measuring this physical distance variation, psi of t. What happens now when this classical gravitational wave is not classical anymore and it's quantized? So the first thing that happens is that this Hij gets a hat to denote that it's an operator now. But more importantly, what will happen intuitively, again, it's a very heuristic way, is we think of quantum mechanical effects as being driven by fluctuations or having fluctuations. So what we expect is that the variation of this physical distance between these two freely falling masses will still continue to vary with the classical gravitational wave, but the quantum fluctuations on top of the gravitational field on top of the classical gravitational wave will induce this jitter. So it will induce a noise term in the physical distance, psi of t.
I guess even classically, you're not going to have a wave coming through that's like this perfect, smooth wavefront.
Of course, there will be some classical noise sources. In some sense, what we're doing here is idealized because we're theorists, and and this is what theorists do. They look at spherical cows. But in some sense, it's a proof of concept of what would happen if we did have perfect knowledge of the classical gravitational wave signal. Then we would still see this jitteriness. So, like I said, this idea is a little bit heuristic, but turns out that we can make it very precise. And this is what I'm going to try to explain. So first, like we already kind of hinted at it, I'm going to explain how to model a gravitational wave detector. Either gravitational wave detectors like Virgo or like LISA. As I have said before, we're going to model one arm of this detector because it's already complicated enough. Now comes the first equation, because again, I'm a theorist, so I love equations. I try to keep them to a minimum. This detector model is very simple. Yeah, there's the action that governs the dynamics of this system, of the detector coupled to the gravitational field, has three terms. The first one is the Einstein-Hilbert term, which is basically the dynamical action of the gravitational field. The second and the third one are just the actions for two free particles in this gravitational field.
I'm not sure what width of audience will be watching this. So just in case, I guess it's useful to clarify that the Einstein-Hilbert action is not anything beyond general relativity. It is the action that generates general relativity when you take its equations of motion.
Yes, exactly. It's basically just pure general relativity and two freely falling masses. So in a pictorial way, you can imagine that there's a space-time with some background coordinate system. So this grid here, this curved grid, and we have these two freely falling masses. And we know that when you have a mass that's freely falling in general relativity, this means that each of these masses moves on a geodesic of the spacetime. So we have one end of the arm of an interferometer moving along its geodesic, the other end moving along its geodesic. And they're separated by this physical distance vector xi. Another thing that classical general relativity tells us is that if there is some sort of gravitational wave that we call h, then the separation of these two geodesics will obey this equation, which is called the geodesic deviation equation. So basically, the presence of the gravitational wave will deform spacetime in such a way that these two masses will move closer apart and then further apart and then closer apart. So their physical distance will oscillate. So now we have to go a little bit further. We have this action and we have to make some assumptions. And the first assumption is that one of the ends of the gravitational wave interferometer arm is very heavy. This means that because it's very heavy, we will neglect its own dynamics. It fixes, in some sense, the reference geodesic with respect to which we will measure the position of the other particle. Then basically we make judicious choice of coordinates in which the action for the second particle, so for the light particle, looks simple.
It looks like it's essentially that one of the particles is sitting at the origin and the other one is then its coordinate is the proper distance.
Yeah, exactly. So basically this is called Fermi normal coordinates. Basically we chose the heavy particle to be the origin of our coordinate system.
This heavy light particle thing, I guess, is not something that is correct for LIGO itself.
Yeah, it is not correct for LIGO or for LISA. The reason why it's not that wrong, and in some sense we were just being lazy. So doing this is equivalent to saying that we're neglecting the motion of the center of mass of the system of two particles. So it's a kind of a two-body problem thing. You can either consider that one of the bodies is heavy and you can put it at the origin and look at the motion of the second body in the frame of the first, or you can treat the full motion of the two-body system by first looking at the center of mass reference frame and then introducing a reduced mass and blah, blah, blah. So you can do it properly, but it introduces complications that do not bring anything new.
Right. That might be relevant if someone's actually 30 years from now going out to measure this, but to show that it exists, they're not relevant.
Exactly. And if I had to guess, there wouldn't be any interesting effects coming from that. So yeah, once we do that, we can do another approximation. Consider that the gravitational field is weak. So basically that the metric is very close to the Minkowski metric, to the flat metric. Take a particular gauge for this metric perturbation, h mu nu, which is called the TT gauge. TT means transverse traceless and is the classic gauge that we use when we look at gravitational waves. And then do a bunch more approximations. Consider a dipole-like approximation, take a non-relativistic limit, and expand the previous action in xi, so in the physical separation. And by keeping the lowest possible orders that still give us an interaction between the gravitational wave interferometer and the gravitational field, we get the following. The full action reduces to this. The first term is just the Einstein-Hilbert action expanded at quadratic order in this particular gauge. And the second one is a very interesting term because, of course, it's a very approximate term, but it looks like it's a free particle. So the kinetic term for a free particle, half mv squared, basically, plus sort of a cubic interaction, which couples the second derivative of the gravitational field perturbation to the square of the physical separation of the two masses.
Can I ask you a quick, possibly again, stupid question, but possibly not, about, say, you're expanding it in quadratic order, but up until now I'd been imagining it as a kind of dimensionful quantity. It's like the physical distance. It has a unit of meters or whatever. Why can I only expand it in quadratic order? What am I missing there?
So the proper perturbative parameter is not, of course, psi, because it's dimension full. But the idea is that you want to compare xi to the curvature scale, to the local curvature scale in the vicinity of the heavy particle, for example. So as long as xi is much smaller than the local curvature scales.
Okay, and so this equation you've written here now, has psi somehow been written in some sort of natural units where the curvature has been factored in? Otherwise, is the small quantity in the actual action you've written?
Yeah, there is a scale here, which is in some sense like I said, the curvature scale, which is related to the wavelength of the gravitational wave that's incoming.
If I change the wavelength of the gravitational field, I guess it changes the h double dot in some way. Maybe that's what it is. It's that h double dot times xi is the small thing, not xi.
Yeah, exactly. So it's a bit hidden here in the sense that the stuff that we're comparing xi to is included in h. I am going to come back to that a little bit, but I agree with you that this is a very legitimate question, I think. And
yeah, it's just that all the other approximations you were saying you would do, I could immediately kind of see what the small quantity is.
this one is related to the dipole approximation that I'm talking about here. So basically it tells you that you cannot, in this framework, consider wavelengths of the gravitational field that are smaller than the physical separations of the two masses that you're looking at. That will immediately limit the amount of modes I can have in H. I won't be able to look at very high frequencies. So the point is that this is the action in the relevant approximations that we will use to try to make sense of what the quantum effects of the quantization of H on the separation of the two masses Xi are. I should mention that at this level, this action is completely classical. We haven't done any quantization yet. So we will now, because we're doing quantum field theory after all, I couldn't help but draw a Feynman diagram. The idea is the following. Of course, because we want to couple this gravitational field H to the separation between the two masses Xi, we will need to quantize both. In the end, though, we will take the limit where Xi is classical, because we know that the two ends of the detector are more or less classical. But the basic process, the basic elementary process that's happening when a gravitational wave hits this detector is the following. The initial quantum state of the detector is this ket capital A. Its final state is ket capital B. And we're interested in how the detector transitions from the initial state to its final state under the influence of an incoming quantum gravitational field. So this is kind of the Feynman diagram that we're interested in. The key point is that we do not measure the final gravitational field, so the outgoing gravitational field after this interaction. So this guy is unknown. However, this guy we can do calculations for many different incoming gravitational field states. Another feature of this Feynman diagram that's very important is that it contains all these loops, but it doesn't contain any other kinds of loops like pure graviton loops or pure detector loops. The reason that it doesn't contain pure detector loops is because the detector is taken to be heavy, so the loops are suppressed. The detector is very heavy, it's in order of tens of kilograms. And the reason it doesn't contain pure graviton loops is because there are no interactions here that would give you pure graviton loops. You would need something like h squared Xi. The detector involves all these processes, but what we are interested in is in calculating the transition probability from the initial states of the gravitational wave interferometer to the final state of the gravitational interferometer, given an incoming gravitational field in a state psi and within some time. And since the final state F is unknown, we have to sum over all final states, as we often do in quantum field theory. It turns out that you can evaluate one of these amplitudes via the path integral formulas. And I'm writing it just very schematically here. So it's just you do an integral over all possible separations of the two detector arm ends. So in any case, there is this path integral representation of this particular amplitude here inside the square.
And I guess the crucial part is that you have an e to the I s over h bar, and s is the action, and the action has those terms in it.
Yeah, and the crucial part is that this way of calculating amplitudes is weighted by this phase, which involves the action. So when you use this path integral formulation to express this transition probability, what you get is this. Okay, it's a bit complicated, but the idea is that it will be a double path integral because of the square. So here, if each of these guys is a path integral, then the square will be a double path integral. And over xi and xi prime, weighted by this particular term, which looks kind of familiar because it's the path integral of a free particle for xi and 1 for xi prime, and then multiplied by this quantity here, which is called the influence functional. Why is it called the influence functional? It's because we hid all the h dependence coming from this particular path integral here and from these terms in the action. We hid it in here. So it's basically this functional encodes all the quantum effects of the gravitational field. So in some sense, everything is in here. Of course, we haven't done anything yet, so we need to calculate it. And of course, this influence functional depends on the initial state of the gravitational field. And you can write this influence functional also in path integral formalism. Basically, it's just rewriting this formula by plugging all these things back in. So now, I'm not going to get into the details of how we calculate this because it's a bit messy, but we are able to calculate this influence functional for different incoming gravitational field states. And let me explain what the result is. So if I take my gravitational field to be a so-called coherent state, a coherent state is a state that is a quantum state that most closely resembles a classical gravitational wave. So if I take psi to be a coherent state that contains this classical gravitational wave h of t, then the influence functional will look something like this. There will be this quantity here, which turns out to be the influence functional for the vacuum times this particular phase factor. And this quantity here, this vacuum influence functional, encodes two different effects. So it's a complex quantity. Its argument, which has this expression, but it does not matter that much, encodes dissipation effects, because you can think of the gravitational field as being a bath of gravitons. So because it's a bath of gravitons, the interactions between the detector and this bath of gravitons will be dissipative. So there will be an infinite number of modes, and there will be some dissipation. And the modulus of this vacuum influence functional given here will basically be encode fluctuations. And I'm gonna tell you why.
In terms of this slide here, what does it mean to say that H is in a coherent state? I mean, I remember that a coherent state is essentially, it's like the eigenstate of the annihilation operator or something like that, but that's not translating very well to understanding what it means when you slot it in here.
Okay, there's two ways of talking about this. So one way is that a coherent state is a Gaussian state, is a particular kind of Gaussian state. Because it's a Gaussian state, and because these actions are no more than quadratic, I can actually do the exact integral. This will just be a bunch of Gaussian integrals, complicated Gaussian integrals. It will be Gaussian path integrals and Gaussian normal integrals, but it will be Gaussian integrals and it will be doable. So that's one way of looking at it. There's another way of looking at it, and I have a slide on it, where you can rewrite this in canonical formalism. So you see I put the Bourbaki dangerous bend sign. I don't know if you know what that is, okay. But here, anyway. But it turns out that you can rewrite this influence functional in a canonical way, where these time evolution operators, which looks much more simple, except it's not that simple. These time evolution operators only correspond to the gravitational part of the action. And once you do that, you can decompose the field, the gravitational field, into modes and quantize each mode of the gravitational field. And then you write this influence functional in this way, where this product is a product over the modes of the gravitational field, the quantum gravitational field. So what does it mean for the quantum gravitational field to be in a coherent state? Well, it means that each of its modes is in a coherent state. So if I put this guy, if I replace this guy by a coherent state, because, as you said earlier, the coherent state is an eigenvector of the annihilation operators, then these annihilation operators, even in the exponential acting on the coherent state, will just pull out an eigenvalue. So they will be replaced by these operators will be replaced by a scalar.
Right, and the same with, I guess, the a dagger operating to the left.
Yeah. Yeah, so I guess the takeaway is that we can compute this influence functional quantity for the case where psi is a coherent state. So psi is the quantum states that correspond to a classical gravitational wave hitting the detector.
Is there a quick, concise way of explaining why the coherent state is closest to the classical?
Yes, there are a few maybe, but the coherent state is a state whose wave function is Gaussian. Our intuition likes Gaussian states because they're kind of localized, and we know that a classical object will be localized. It won't have two bumps, for example. So one thing, it's a Gaussian state, but secondly, it's a Gaussian state that saturates the uncertainty relation. You won't be able to measure delta x and delta p more precisely than for a coherent state. After we calculate this influence functional in a complicated way, we are able to look at this prefactor, which turns out to be the vacuum influence functional. You can see that immediately, that if H is not there, so if there is no gravitational wave, then this guy goes away, and this is just the influence functional of the vacuum. And this influence functional of the vacuum encodes both dissipative effects and fluctuation effects. And this will be very important. In particular, the fluctuation term, which has this particular kind of quadratic form and involves this function a of t minus t prime, it can be rewritten via a clever trick as the average value over some quantity n of this exponential here. And this is very important. It might not mean much for the moment, but this explains why this is the fluctuation term. Because as you can see, this term inside the brackets looks a little bit like this term, except the derivatives are here, yeah. So this capital X is the second derivative of xi squared. So it looks kind of like this term, except this quantity n of t is a stochastic quantity. Is a quantity that we average on. So it's a noise term.
Okay, and n is some thing that depends on a.
Yeah, and n, yeah, and that's a very good point. A turns out to be the autocorrelation function of this function n of t. A is basically what gives the statistical properties of n. Yeah. Maybe I forgot to say that n is a Gaussian noise. This is a Gaussian average over the function n, where the Gaussian probability distribution of n of t has autocorrelation a.
For details, see the paper.
Yeah, exactly. But this is kind of important. So now this is the final, almost the final result. The transition probability that we're interested in can be written in this way. This term here is just the averaging procedure over the Gaussian noise n. You see that this is a Gaussian distribution over n, and the integration here is basically just averaging what comes next with respect to this Gaussian distribution. We see here that a is indeed the autocorrelation function.
So this is just expanding the average bracket. Yeah.
The next terms are given, so this term we had from the beginning is just the phase corresponding to the kinetic term of the free particle. The second term comes from the fact that we have a classical gravitational wave propagating, and this term is the dissipative term that I haven't talked about too much. And finally, this is the fluctuation term that involves this function n of t. So now I said the last step is that I said we need to take the limit where the detector is classical. So in the path integral formalism, the way we do that usually is that we take a so-called saddle point approximation of the path integral. So this saddle point approximation gives us an equation of motion for xi, and this equation of motion looks like this, and this is the final result.
This is heuristically kind of, instead of the path integral is summing over all possible paths, giving relative amplitudes to that phase term, and then what one does now is essentially just taking the most probable path.
Exactly. It's kind of like what we do when we vary an action. When we vary an action, we say that the classical path is the path that minimizes the action. In a path integral, the path that minimizes the action is also the path that is the most probable. So this is exactly what we're doing. So we're taking the path that is the most probable, and the path that is the most probable will obey this differential equation. If you forget about these two terms, the n term and the fifth derivative term, this is just the classical geodesic deviation equation. But now it's not the classical geodesic deviation equation, because we have included all the quantum effects coming from the gravitational field, the quantized gravitational field. We have the fluctuations coming from the quantized gravitational field, which give you this n double dot term, which is a noise term. It's a Gaussian noise term. And we have this complicated looking term, the so-called radiation reaction term. And that's also encountered in electromagnetism. When you have an electron that moves, that is accelerated emits waves, so loses energy.
And so, like, it's a quantum effect, you mean, or is this pure classical EM? You'd have this term.
In this case, so that's quite puzzling because you can talk about the radiation reaction classically, but here it arises purely quantumly. So there's probably a very deep quantum origin to radiation reaction, even in electromagnetism. But this term won't be very important because it's very complicated and we don't really know what to do with it.
It looks like it'd be quite small as well, right? Because you'd need, I mean, it seems like it's some sort of like almost back reaction term, right? Like that, like if the mass was very, very heavy, it would be generating its own sort of gravitational waves. But here it's
exactly.
too light. M is too small.
So that's the idea. The idea is that the two masses start moving under the action of the incoming gravitational wave, but because they're moving, they're emitting their own gravitational wave, so they're losing energy, blah, blah. But this is a very small effect. And we don't quite know rigorously how to show that it's very small because of these fifth order derivatives.
I see. So even though mg over c to the 5 is small, it doesn't mean that d5 dt5 is small, right?
But on physical grounds, we expect it to be very small, like you said.
Okay, I'm convinced. I don't know. If the viewers aren't, then they can write angry comments.
This is called the Langevin equation because it has this noise term. But it's basically the quantum modification of the classical geodesic deviation. And now for some observational consequences. So we can analyze this noise term here because we know how to calculate the statistical properties of the noise. That function a of t minus t prime that I was talking about earlier is the autocorrelation function of the noise. This gives you the spectrum of the noise. The Fourier transform of the autocorrelation function is the spectrum. And we can calculate the spectrum of the noise. And from the spectrum of the noise, we can estimate the size of the noise. And the size of the noise is just the integral of the spectrum, basically. The problem is that the integral of the spectrum, in our case, diverges, as we expect, because in quantum field theory, you always get UV divergences. So we need a cutoff, a high frequency cutoff. And it turns out that there is a cutoff that is naturally present in our problem, because remember at the beginning, I said that...
the dipole approximation?
Exactly, that this is valid in the dipole approximation. So I cannot consider frequencies that are too high. I can only consider those frequencies that are high enough, but still maintain the validity of the dipole approximation.
But that doesn't mean that those frequencies aren't contributing. It just means that you couldn't calculate them, right?
That is true, but in this case, you have to imagine that our detector has a limited sensitivity. In general, gravitational wave detectors operate within the dipole approximation. What's the reason that LIGO is sensitive to the particular frequency band that it's sensitive to? Well, the main reason is that it has an arm length of the order of the kilometer. If it wanted to be sensitive to higher frequencies of the gravitational waves, it would have to have a shorter arm length. But with a shorter arm length, it wouldn't be sensitive enough for technical reasons. LISA is the same. So LISA has a longer arm length. So this means that it's sensitive to lower frequencies. So at this point, the highest frequencies that we have access to in terms of gravitational wave detectors are with LIGO and Virgo.
I mean, yeah, that definitely from a heuristic sense feels correct. But from the kind of maths that's being presented sense, it feels a little bit uncomfortable that omega max, if you're telling me this integral diverges, I'd have thought that the calculation should notice that physics that you just described, and that therefore, as you increase omega max, the noise term decreases.
Yeah, so that's not the case because, well, first of all, because we do not have a proper theory of quantum gravity. Yeah? So we don't know how gravity behaves at very high frequency. Right now, we're doing a kind of baby steps into quantum gravity when we use these methods, called perturbative quantum gravity. We're not doing string theory of loop quantum gravity or crazy stuff like that because we don't know how to do them, but also because in this case we don't need to. In other words, you always have to think that this quantity psi of t will be a convolution between the detector response function. Maybe I don't have the right terminology here, but
sure.
Some detector sensitivity and the actuals. So this is kind of a very crude convolution, if you want, when you have a hard cutoff. Yeah, so the point is that for different states, we will have different spectra of the noise. And with different spectra, we'll have different noise sizes, noise amplitudes. And So we have calculated the noise spectrum for vacuum and coherent states, which is here. We have calculated it for thermal state, which might be very interesting for cosmologists because we know there should be a cosmic gravitational wave background, and not just that, but many stochastic gravitational wave backgrounds. Some of them might be thermal with some temperature, which we estimate to be probably very small. But anyway, the spectrum of the noise coming from such a background would look like this. And we also did it for something that's the most promising, which is called squeezed states. So a squeezed state is also a Gaussian state of the gravitational field, but it's a Gaussian state that behaves more quantumly. So remember how I told you that the coherent state is a state that saturates the uncertainty relation? But it saturates it in a way that the uncertainty is evenly distributed between delta x and delta p. A squeeze state is also saturates the uncertainty relation, but the uncertainty is not evenly distributed. It can be very squeezed in one direction, in the x direction, and unsqueezed in the p direction, for example. And I think in cosmology, these things are quite important. And so such squeezed states of the gravitational field can arise from cosmology. And if the squeezing is large enough, then there is an exponential enhancement. So this is the most hopeful.
Yeah, the inflationary perturbations from a certain perspective are squeeze states. That's interesting.
Exactly. So that's the hope that we would get enough squeezing. Because right now, I haven't actually given you estimates of the noise, but we can estimate for each of these cases, we can estimate the noise. And for the case of vacuum and coherent states, the noise is tiny, basically Planckian or sub-Planckian. For thermal states, it's a bit better, and it depends on the temperature. So here I took, for these estimates, I took a temperature of the order of the CMB, sort of a cosmic gravitational wave background. This is better. This is only at best 10 orders of magnitude more sensitive than our current detectors. Better than the 40 orders that Dyson was mentioning. But for squeezed states, you still have this exponential enhancement. So depending on the amount of squeezing that you get, in particular for fields that arise during inflation, you could have a very high squeezing.
Yeah, I mean, my naive immediate question would be, what axis is cosmology squeezing on, and what axis are you squeezing on to get this? Because it could also be an e to the minus at if cosmology is squeezing along the wrong direction.
That's a good point, and this is something that we are actually in the process of looking at.
Okay, well, I'll interview you on that next year.
Given how long it took for these papers to come out, I don't know, it might be in 10 years.
Yeah, fair enough. Okay. I'll interview someone else in a year then who's seen this talk and scooped you.
So the most hopeful scenario is the case of squeezed gravitational field states that might actually have a quantum noise that is measurable. The things that we did in this series of papers was to reduce a gravitational wave detector to its most simple essence, which is basically just the arm length of the of the detector, and that's it. And to couple that arm length to the gravitational field, to a weak gravitational field. And by doing that and quantizing this weak gravitational field, we found a modification of the geodesic deviation equation that is a Langevin equation, so that involves a noise term. And this fundamental noise term, we were able to calculate its different characteristics and to estimate how big.
And I guess the important thing is you've done it for the coherent state and the squeeze state and the thermal state, I guess. And from that, you get order of magnitude numbers. And again, like if someone actually detected this and wanted to make a very precise statement, they might have to do it for the exact form of the incoming wave. But obviously, whoever gets there first gets to make all the initial approximations. So
yes, so one of the nice things about this noise is that if you take, for example, two gravitational wave detectors and put them one next to the other, they should both see the same quantum noise. Because a question that you could ask is, okay, there's this noise, but how do we distinguish it from all the myriad sources of noise that exist in the gravitational wave interferometer? So one way is to use the fact that the noise will be correlated between different detectors.
yeah, although if detectors are too close to each other, they might be still correlated. Like if there's a truck going past, it might shake both of them. I don't know.
Yes, that is true. But
It'd be correlated. Yeah, I mean, I think that's fine. It's correlated in a particular
It's
way. That's,
correlated and it has a particular spectrum, which is different from most other noise sources.
I was thinking the way you detect it is the same way they detected the CMB. You just keep trying to remove noise until there's some annoying, painful noise that just won't go away, and then realize that you've made a Nobel Prize-worthy discovery.
Exactly.
Which would be, I mean, this would be, I don't know, it's hard to think of something that's more significant than detecting the CMB, but this might be a leading candidate if you detected the quantum nature of gravitational waves. I think that's pretty earth-shattering.
I think so. I think it will be amazing. I'm not super optimistic that it will be detected in the very near future, but I do believe that our methods are sound and they do not rely on any exotic physics.
Cool. So I guess we've just been talking about this a little bit, but is there anything else? Where to next? I guess you were saying you're looking into this squeezing. Is there anything that whoever's building the next gravitational wave detector should keep in mind that other than just noise?
So first of all, having gravitational wave detectors that are sensitive to higher frequencies would help smaller distances. So maybe tabletop experiments. I don't know much about it, but that would be helpful. Another thing is to kind of try to design the experiments to maybe somehow be sensitive to these kind of correlated noises. So not try to eliminate as much as possible.
It feels like you'd want to eliminate the noise, but your like analysis would want to focus on the noise.
Exactly. Something maybe the pipelines would need to be rethought, or I don't quite know because I'm not really an observationalist. But that I think it would be interesting if we had access to higher frequencies in future generations.
Cool. Well, hopefully, yeah, 10 years from now, I'll be interviewing some person with a tabletop gravitational wave detector who's just detected quantum gravity. Oh, well, we'll get ahead of ourselves. Cool. All right. Yeah. Outside of your own research, what do you think is the most interesting thing? And the normal question is in cosmology. I guess you're a cosmology adjacent, so you could talk about just fundamental physics if you want, or if you've got something that you like about cosmology, you can also mention that.
Yeah, so maybe a few things. Well, obviously in cosmology, there's this, which I don't know, maybe people are understanding it better nowadays. This H naught tension. I've read lots of papers with different possible solutions. So I think that is something that is very puzzling and very exciting. Hopefully, it's not just some systematic effect. But more generally, I think the thing that excites me the most in fundamental physics and in cosmology adjacent stuff is the prospects that are brought up by gravitational wave detection. You can do a lot of things, not just this.
Yeah, yeah, yeah. And it's so new.
Thinking of using gravitational waves as an early warning system for supernova explosions. There's this, of course, this very recent nanograv thing about pulsar timing arrays maybe having detected gravitational waves that maybe could come from cosmic strings.
Yeah, 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 yeah.
I think, honestly, I think gravitational wave have opened a new realm of cosmological and physical.
Well, thanks everyone for watching. If you like this, don't forget to subscribe and click the bell if you want to be notified when a new video comes out, and click like to help with YouTube algorithms and all of that. More importantly, share the channel with your colleagues in this video if you found it interesting. If you have any questions for George, leave a comment, or if you have suggestions for future videos. While you're here, you can watch another video. Normally, I've managed to work out what a closely related appropriate video is by this point, but I don't have any on my mind, but some will be appearing right now on your screen. So if you find them interesting, click on them. And thanks again, George, for the great talk.
Thank you.